Okay, welcome back to session 8 on digital circuit design using ADS. So what I'm going to do is in this session I'm going to design differential flip-flops, and they are going to be quite useful for two reasons. A, they can be operated at much higher clock speeds than compared to the just the single-ended ones, and second thing is then the noise thing which I have already mentioned, right? So let's go ahead and do a new schematic, and I want to do differential D flip-flop, and I'm going to do a MS or medium speed. Create schematic. Okay, so it's just that there are two paths instead of one now because it's a differential, and then there are differential NOT gates, right? So basically the forward path will have two of this, right? Okay, and then you would need two of the transmission cells instead of one, so TXL. Okay, so you need two of these for the forward path and the feedback, right? So I'm going to connect 1 and 2. Okay, so there are two of these, and I will keep all the supplies away. So again I'm going to copy these, and then I am going to flip this, and there are two of this which are going back. Okay, so now the design is very simple. Okay, so I'll just do the forward path. So I'll come in this way as D, and this will go out as this way, and then this will go to the feedback, and it will come to here. Done. And similarly I'm going to take this one, okay, which is going to go this way in this path, and it's going to come out here, and I'm going to do a feedback here. So I'm done. Okay, so this is going to be the master, and then I'm going to have a slave. So what I'm going to do is, okay, so I'm just going to copy this. Okay, before that I'm just going to name some of the things, like for example you have VDD, and then you have ground. So at least these two go by copying from master to slave, so that's why I'm doing this here. Sorry about this. Okay, so this is VDD, so this is VDD, this is VDD, this is VDD, this is VDD, again here VDD. So we have covered all the VDDs, and then we will go to ground, and we will cover all the grounds. So this is ground, this is ground, 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 ground. Okay, and what I'm going to have is a clock and a clock bar. So I'm going to have a pin which I'll call clock. Okay, and then I would have an inverter. Okay, so I would use just a single inverter, right? So let's go to static, and let's look for an inverter here. Medium speed, NOT gate, MS. So that's the one. So I want this over here. Again I have a clock and I have a clock bar, right? And then I'm going to have VDD, and I'm going to have ground. Okay, so I'm going to name this node to be small CLK, and then this is going to be CLKB. Okay, so if I want to do, so basically I am going to have a clock here and clock bar here. So clock bar here, clock bar here, and they are in tandem, so they are going to be over here and here. And then I'm going to have clock and clock, and then they are in tandem, so it will be over here. So this is the master, and I'm going to copy this entire thing and paste it on the other side like this. And what I have now is this going here, this going here, and I have to reverse the clocks here, right? So this will be clock B, right? So I'm going to say name node. So this is going to be clock B, and this is going to be clock B, and this is going to be clock B, and this is going to be clock B. This is going to be clock, this is going to be clock, and here it is going to be clock and clock. So basically this is master and this is slave. So we are done with this, and then we are going to have D bar as the input. So I'm going to have D bar as the input. So I have a D input over here, and I have a D bar input over here, and clock is already taken care of. So I have a differential path going in and a differential path going out. So I need 2 pins, a Q, and I will have a Q bar. Okay, so very simply put, this is going to be my differential D flip-flop. Okay, let's just verify this. So everything looks correct to me. Only thing which you can mess up is clock bar, clock bar, clock bar, clock bar, clock bar, clock bar, clock, and clock bar. Okay, so this is all that's done. Let's make a symbol for this one. So I have a PPCL, so differential D flip-flop MS, right? So I need a symbol for this, new symbol. Okay, I'm going to keep it on the side and just make my symbol here. Sorry. So I don't want to make a big stuff out of this. So D bar comes over here, Q bar comes over here, and ground rotates out to the bottom like this, and VDD and clock. So VDD goes up like that, and clock to the bottom. So still I can save some space by shortening this guy. So I don't want it to be very large, right? So that's there, and just I'm going to do the edge thing for this. So I will turn off the grid and shrink this slightly just to put a circle there. That's the bubble for negative, and then you want to show that it's a negative edge. So I'm going to put here something like this, which will show that this is an edge triggered. I will turn the grid back on. Okay, so I have here a D flip-flop which is differential. Now I'm going to make a high-speed version of that. So I'm going to say copy cell. So I want to copy only differential HS, and this I will copy to the high speed and say OK. So once we are done with this, I'm just going to modify this. For all I had to do is change everything to HS, and it will just add it in place. So I'll go from left to right so I don't miss anything. Okay. Okay, by the way, where would I use this? Okay, people might think that I might make a counter out of this and stuff like that. Resettable counter. Yes, I would make a resettable counter out of this. Another thing I'm going to do is I'm going to make left shift and right shift registers. So I will do a left shift feedback register, left LSFB, and that would be your PN sequence generator. So I want to generate PN sequences, right? If I was to use some form of a communication where I need PN sequences, I can generate PN sequences from a PN sequence generator. Next thing is I'm going to make a 2x3 cell out of this. So that is going to be a prescaler for a PLL. So nothing is going waste for here. You might think it is very fundamental, but it will be used in the larger circuits. So you somehow make your libraries. Actually, you should also make a layout also, so that you can develop much bigger circuits much faster this way if you make a library with the layout. This I recommend in Cadence. You can do this if you have a library access to a PDK and Cadence. Okay, so we are done here with all the in place edits. I don't want to miss any one of them, right? Okay, we are done. So all I'll do is I'll just modify this to insert a text and call it HS. Okay, and then I want to test this. I want to test this in the same test benches which we did for the single-ended ones. So what I'll do is I'll go to test PPCL NAND is there. Now I will pick up a flip-flop medium, and I have a testing of D flip-flop over here, right? So I'll copy this cell, copy cell. So I'll just copy the test bench. Yeah, this is the one which I want, and I'm going to call this as DFF MS, and I'm going to copy this to PPCL medium speed. Okay, so it is copied over here, diff. I'm going to open this. So that's a regular D flip-flop, right? So I am going, okay, I modified it earlier for T, so it doesn't matter. So I'll name this as D, doesn't matter. Sorry. Okay, we are, and I'm going to insert the D flip-flop over here. That's the one. So do not worry about this stuff. Don't worry about this. So all I'm going to do is copy this over here. This is Q, and I'm going to copy this over, sorry, I'll just copy this capacitor as a load. And this will be Q bar. Okay, so this is Q, and name node, this is going to be QB. Okay, so I operated it at 2 gigahertz, right? Now this is a clock, so what happened with the clock? Okay, fine. So operated at a clock of 2 gigahertz, right? And this D was at 0.125 gigahertz. Fine. Okay, so I'm going to do a D bar, right? So I am going to just copy this. I'll make a bar out of this one. So that's a D bar. It says the same frequency, but I'm going to add a delay of 120. Sorry, I'm going to add a delay of 4. So right now this is 3.9, right? So this is a delay of 4 nanosecond. Okay, so that's going to give you the differential input. Okay, and I will call this as D bar, dB. Okay, so I'm going to go ahead and bump up the clock frequency to 4 and see what happens. So when you bump up to 4, this will become 12.5. Okay, 5 like this, and I will do a 4 on this, and I will change this frequency. Okay, so I have bumped up the frequency here. This is a differential in. This is going to be on the falling edge. So there is a decision on the rising edge on the master, right? So I'm going to introduce a slight delay in the D. That will be half of half. So 120.125 nanosecond, right? 0.0625. 0.0625. And here also a delay of, okay, so I have to add that delay, right? 0.0625. Done. So I have generated a differential D with a delay of half the 1/4 of the time period here, right? So okay, so it makes sense here, nothing special here. Okay, let's try to operate this. Let's see what happens. If we've done a blunder, we will come to know that. Simulate. Yeah, for first time, ADS takes time. Okay, we are done. So first I'm going to see whether my D input is okay. So D goes here, D bar goes here. So this is your D, this is your D bar. So they are out of phase, right? And then there is a slight delay here, right? So let's put here clock. Okay, so that's the clock, and I want to verify that this D transition has been delayed by 1/4 cycle here, right? So that means that the falling edge comes in somewhere here, right? So there will be an update on the falling edge. Okay, but then it will be red on the rising edge, so this might come low. So it might happen over here that you get a high. So let's check that. Okay, so I am going to put here a Q. Okay, so let's see. As I was saying, the transition would come on the falling edge, right? Okay, so I am going to separate them out, and I'm going to delete D bar, and that's it. And I'm going to turn this to be a green color so it's visible clear, and I'm going to separate them out. Split the trace. So that's the splitting of the trace. Okay, so this one I'm going to put blue color. Okay, so whenever there is a falling edge, so on the falling edge there is a transition here, right? Okay, let's also do this for clarity. Okay, so on the falling edge there is a transition, so this follows that on the falling edge. So for visibility I'm going to expand this so that you can see what I'm talking about. Okay, so if you see, I'll put a marker which is over here. Okay, so of course there is a delay, right? So on this falling edge, are you sure that's what is? Yeah, but let's look at the clocking. I think this should happen on the falling edge, but it may be a delay, right? So let's look at the clocking. Yeah, so it makes sense. So what is happening is these are going to go through on the positive level of clock, and this will be disabled, and this is going to go through on the negative level of clock, and this will be disabled. So master will respond to the positive clock, and the save will respond to the negative clock. So there is a delay. Okay, so that's the delay what you are seeing, but this is going to be hazardous for a circuit. So you cannot operate this circuit at 4 gigahertz because you don't have a margin here. It's doing this transition on a positive, so there is a quarter cycle delay. So maximum frequency cannot be 4 gigahertz in a larger circuit, though for demonstration purpose it's okay, right? Because there is something called a setup time here, right? So that is violated, so you cannot operate the system at that 4 gigahertz. Okay, can I speed this process? Yeah. What is slowing down your process? These positive feedback can be made faster, or the output capacitance can be reduced somehow, right? Another thing is that you can make this to be a large devices, but then you have to drive higher capacitance, higher resistances, right? So RC delay is going to improve, but capacitance is going to add up, right? So all these things you have to keep in mind. So what I have just demonstrated to you is it cannot be used at 4 gigahertz, though I'm simulating it, because you should have a certain setup time which should be before the positive. If I have a transition at positive, that means that this circle will fail in the larger circuit if you use that at 4 gigahertz. Anyways, so these delays, what they mean to you. Okay, now let me do this. Okay, let's remove that delay and let's see what happens. Okay, so let's say this delay was 0 and this delay wasn't there. Okay, so let's see what happens to the transitions. So maybe quarter was too much. Even if it moves by quarter to the left, does it? Yes. But what margin did I get over here? Did I get any margin over here as a setup? Slight. Is that enough? No, it's not enough. It has to be a transition on the falling edge, right? Okay, so you understood the concept of critical path and maximum frequency of operation. Stuff like that would happen because of this. Okay, so I'm going to very quickly change this. Okay, close this. I'm just going to copy this cell. So this I have already done, right? So I have this version. So there is a test bench which I'm going to copy. Test diff. Okay, copy cell. Okay, and I'm interested in test diff ms. I'll make this as hs, and I'm going to put this in the high speed folder. and say okay. So test bench is over here. This is not, sorry, test diff, that's the one. And I am going to change this to HS, change this to 2, this to 2, and I am going to change this to maybe 40 gigahertz, right? 40 gigahertz. Then this will become 12.4 pico, 12.4 picosecond, and this will be 0.1 picosecond is the rise time, and 0.1 picosecond is the fall time. So that's taken care of. And this one is going to be 1.25 gigahertz, 1.25 gigahertz, and this would be 400 picoseconds, so 399 picosecond, and this will be 0.1 picosecond and 0.1 picosecond, and this will be 400 picosecond delay. Okay, and over here the same stuff, 399 picosecond over here, and this is 1.25 gigahertz, 1.25 gigahertz. And hang on a second, 399 picosecond, I can do a rise time of 1 picosecond, sorry, and over here 399, 1 pico and 1 pico. Okay, so this looks right to me, and this looks right to me. All I have to do is take out these guys, Control C, Control V, put them here, delete this guy, oh come on, delete this guy. So we are all set for high-speed simulation of this, and I'm going to simulate for 1.6 nanosecond, 0.6 nanosecond, with a step of 1 picosecond. Okay, sometimes typing mistake. So we are all set. So let's hit simulation. And I'm going to copy the data display window. So that one is open, right? So I'm going to copy this guy. Control C. And when the new data display opens, I'm going to paste it. Oh, do I need to go that slow? Because I have done this mistake, so I'm going to stop this simulation. I need not go that slow, right? This is this, because there is a mistake here. 12.5, 12.4, 0.1 rise time, 0.1 over here. That's okay. 0.1 picosecond, 1 picosecond, that's fine. Let's run this again. This time it will be much faster. So you can make a T flip-flop out of this D, which I'm going to make, but I'm not going to use it. I'm going to use it when I do counters. So I can pause this so that I don't waste your time. So we are almost there. Okay, so I'm just gonna go and paste this. Okay, so it is doing the same stuff. Let's see the margins over here. Okay, so let's see. So this is coming on the falling edge, and this is not as bad as the previous one, because you know, half of this I have gone through the transition already, right? And when the rising edge comes, I have already transited, so I have a hold time there, or setup time, sorry. I have a setup time over here, a lot of setup time I have over here. So this can be used at 40 gigahertz in a system, but again you have to see in a system what is the critical path delays, and they should not go beyond the quarter of the clock. Okay, so that's how your rough clocking would be done, roughly. Okay, so we are done with this. Let's look at a T flip-flop out of this D flip-flop. Okay, so I'm gonna make a T flip-flop out of a D flip-flop. So PPCL, okay, PPCL differential D flip-flop, right? So we were looking at PPCL. Okay, remainings can be switched off. Okay, so over here I have this, so I'm going to make a T flip-flop. Schematic diff TFFMS, create schematic, and I'm going to use a differential D flip-flop, and the clocking is straightforward, only the feedback is slightly different because they are differential paths. So I'll have a VDD, I will have a ground, okay, over here. Okay, so this I'm going to have a XOR gate. I can use a transmission XOR gate. So you see, in transmission I'm going to use a XOR 1. Okay, so I'm going to have two XOR gates. Okay, so I'm going to have two XOR gates. Okay, one of them would be this feedback, other would be this one, and then there would have a clock. So I would have a clock pin over here, and that's the clock. What else do I need? So basically this goes as a feedback over here, and this goes as a feedback over here. Okay, so I'll adjust these. Correct. And these are VDDs. So one is the Q feedback to D and Q bar feedback to D bar, right? And this is going to be the T. So this is going to be the T. So I will call this as T, isn't it? Fine. So clock. Okay, so just name these VDDs. So this is VDD, this is VDD, this is VDD, and this is VDD, and this one is ground, this one is ground, this one is ground, and this one is ground. And then I need Q and Q bar, so I have Q and I have a Q bar. Done. So I'll just connect them. Okay, So this is there. Now what I'll do is I want to test it, right? So I'll just use it in the D test setup. Anything mistake? Nothing. So this is a T flip-flop which is differential. Close that. Do I have to make a T flip-flop? I have to make a symbol for this one. New symbol. Okay. Okay, so in this session, in this whole series, you have to make a lot of what you call you have to make a lot of these symbols. So it will have a T input and it will have a Q and Q bar output, and it will have a clock input, and it is going to have a ground, and it is going to have a VDD. Done. So there is a lot of space in the symbol which I don't like, so let's shrink this. Maybe I can shrink it this way too. Correct. It's not going to kill me. Okay, and this one over here, so this looks better. Come on. Okay, so this is centered. Okay, I want to add, I still don't like this, can be further smaller. Okay, I want to add a bubble, so I'm going to turn on off the grid, shrink this a little, shrink this a little here, add a bubble, that bubble goes over here, and of course slightly bigger bubble, and I want to add a clock thing, so this is the clock thing, this is edge triggered, and I will put back the grid on. Okay, so this is my T flip-flop. Okay, this is my T flip-flop, and I'm going to make a high-speed version of this. So I will just say copy cell, differential T. I will disable all of this stuff, and I will call this as HS. Okay, and this will go under PPCL high speed, and that's it. And then you have a T flip-flop PPCL high speed. Okay, so in the high speed you have one more over here. Yeah, this one, differential T flip-flop high speed. I'm going to add a text here which says HS. Insert text, call this as HS. Okay, so this completes my differential T flip-flop. It's going to be slightly faster than the single-handed copy because of the positive feedback. So I'm going to stop here. Later I'm going to show you shift registers and counters in the next session. Thanks a lot.